Hello there, good morning, good afternoon, good evening, wherever you are. This is Dari on WorldStreams Radio. Thank you to our listeners from around the world for joining us. To learn more about WorldStreams, visit our website, worldstreams.org. You can also find us on Facebook at facebook.com/WorldStreams and facebook.com/WorldStreams.worldmusic, and our past programs are now available on iTunes. Our guest tonight is Lawrence Krauss. Lawrence Krauss is an internationally known theoretical physicist with wide research interests, including the interface between elementary particle physics and cosmology, where his studies include the early universe, the nature of dark matter, general relativity, and neutrino astrophysics. He's one of the few prominent scientists today to have actively crossed the chasm between science and popular culture. Beside his radio and television work, he's performed with the Cleveland Orchestra, narrating Gustav Holst's The Planets in the most highly attended concert at that venue, and was nominated for a Grammy Award for his liner notes on a Telarc CD of music from Star Trek. Hello, Saeed. Hello and welcome, Professor Krauss. It's a pleasure to have you with us on WorldStreams.
Well, hello, Dari, and good evening to you. And Professor Krauss, it's a pleasure to have you with us tonight.
It's nice to be there virtually, sort of.
Thank you, and I know that we will not have time to go over your musical, genius as well, because we will not have time. Well, it all started for you with this idea of nothingness. When one thinks of nothing, what goes through their mind?
Well, I've learned that a lot of different things go through different people's minds when they think of nothing. Most people, ever since my new book came out, obviously I've been talking to a lot of people about this, but most people, I think, would say nothing is kind of like empty space, the kind of nothing
Right.
of, say, the Bible, eternal, dark, empty void with nothing in it. But when you start to think about nothing, then it gets a little more sophisticated. In fact, in particular, as I describe in my new book, if you can get a whole universe out of empty space, if empty space can produce everything we see without any supernatural shenanigans, then people start worrying and say, well, that can't really be nothing, because I don't believe something can come from nothing except by God. So when you tell them that empty space can produce everything we see, then they say, well, empty space isn't nothing. And they say, well, you have the space. Where did the space
Right.
come from? And then you might say, okay, well, let's talk about the absence of space or the absence of time. Is that nothing? Well, maybe that's a little more sophisticated version of nothing. And by the way, I show that the whole universe can come from that as well without any supernatural shenanigans. And the last step might be, well, you don't have space, you don't have time, you don't have the particles, you don't have anything, but you still have the laws, so maybe that's not nothing. And then we have to talk about a universe without laws, which I talk about in the book as well.
Is the notion of time really important to the universe, or it's irrelevant?
Time is not so clear. Time is something that probably it arises, as does space, from the properties of matter, and it's something we don't understand as much as space. It arises, the properties of space and time, ever since Einstein.
Mm-hmm.
Einstein told us that space and time are affected by matter. So you can't really talk about space or time in the absence of talking about what the universe is made of and how it affects it. And because gravity is a theory of space and time, trying to understand gravity within the context of modern physics, which involves something called quantum mechanics, means that even space and time can suddenly pop into existence where they weren't there before, just by quantum mechanical processes. So we could literally create universes, create spaces that didn't exist before. And what is great, and one of the reasons I wrote this recent book, is that all the properties of our universe are, when we look at them, are the properties we would imagine a universe to have if it indeed popped out of nothing.
So what are some of the characteristics of this space? Can we see it?
Well, we can see things in it. The point is we can we put galaxies and other things in our universe, and they trace the properties of space. Our universe is expanding, which is one of the great discoveries that was made about 80 years ago. The universe, because it was one of the proofs that there was a Big Bang, our universe is getting bigger and bigger, which meant, by the way, if we go backwards in time, it was getting smaller and smaller. And we can now work out, amazingly, that 13.7 billion years ago, the Big Bang happened. It's amazing that we can say that with that kind of accuracy. 13.7 billion years ago, the Big Bang happened. And it is amazing that we can say that now. When I was a graduate student, we only knew the age of the universe to within a factor of 2, and now we know it to within just a few percent. So it's amazing.
How do we know that it is 13.7? Is it as far as the eye can see through the...
we use a lot more than that. I mean, first of all, if you were driving a car and you were driving a car at 60 miles an hour you'd be traveling for 2 hours, you'd be 120 miles away. So if you told me that you were now 120 miles away from New York and you'd been driving for 60 miles an hour, I could tell you you'd been driving for 2 hours, right?
Right.
So with galaxies, we can see how far away from us they are, and we can see how fast they're moving, and we can work backwards to figure out how long ago it was before all the galaxies were once together at the same point, and we get 13.7 billion years. But there are lots of other independent ways. It turns out it's not the only way we can determine the age of the universe. We can look at the age of the oldest stars and all sorts of other things, and they all come up with more or less exactly the same number, and that gives us great confidence that we know the answer.
And the way you go about it is very much by calculating the type of light that exists. But these lights tend to be different in their luminosity, right?
Well, I mean, what we do to measure the expansion rate of the universe is we look at objects and we try and figure out how far away they are and how fast they're moving. In order to do that, of course, you have to measure distance and speed, and that's hard to do. Speed turns out to be easy to do, but how do you measure the distance to distant objects? Well, we don't have tape measures that are that long, so we have to use physics, and we'd say, well, look, if we had 100-watt light bulbs, and we could, and we had a light meter here, we could figure out how far away the light bulb was. If it was 100 watts, and we're getting 1 watt of light into our light meter, we know that the light bulb is a certain distance away because light spreads out. Well, we don't have 100-watt light bulbs, and that's the big problem. We don't have the universe isn't populated with 100-watt light bulbs, so we have to find the equivalent, something we call a standard candle, something whose brightness we believe we understand, and then we look at it through a telescope and we see how bright it looks, and then we infer how far away it is, and that's the hard part. But we've been able to find objects called exploding stars, supernovae, whose brightness we believe we understand.
Right. Now, when we're looking at, as part of your, as the director of the Origins Project at the Arizona State University, how relevant is 13.7 billion years to me or to anybody else? Why would that be important?
Well, I think the point is, everyone has asked themselves the question at some point or other, where do we come from? How do we get here? And how did the universe begin? And what's going to happen? I mean, it's not going to produce a better toaster, but it's going to affect our view of ourselves and understanding of ourselves and our origins. And we all wonder about that. In fact, in terms of understanding origins, many people have invented gods to try and understand their origins because the universe seems so weird and inexplicable that people seem to have to invent with their own minds some kind of deity in order to explain things. But more than that, we actually have a cosmic connection to everything. Every atom in your body, every single atom in your body was once inside a star that exploded. As we talk about these exploding stars, supernovae, every atom has experienced the most violent explosion in the universe. We know that because at the beginning of time, the only elements that were created were hydrogen and a little bit of helium and a little bit of lithium. But all the other elements, the ones that are important for your life, like carbon, nitrogen, oxygen, iron, they weren't created in the Big Bang. They were created in the nuclear furnaces and the cores of stars. But the only way they could get in your body and in the earth and in everything you see around you is if those stars exploded. so that the material could be spewed out and 5 billion years ago or 4.5 billion years ago form around our sun and form the Earth and us. And so we are literally star children. And the atoms in your left hand could have come from a different star than the atoms in your right hand. And so really we are cosmic. It matters to us in an immediate sense. We are stardust. And we are the children of the stars. And as I put it in a video that seems to have gotten a lot of interest, I said, forget Jesus. The stars died so you'd be born.
So in essence, the stars actually it gives a meaning to when we say that we are cosmic beings.
Exactly, it really does. We should be intimately interested in this because the material that forms our body it tells the whole is part of the whole history of the universe. And I, as I say, it is amazing to me to think that every atom has experienced this incredibly violent explosion. When a star explodes, it emits as much light as 10 billion stars. I mean, it's hard to imagine that every atom in your body has experienced that violent explosion. So we really should, in an immediate sense, realize we have these connections with the cosmos. But I also think from a perspective of understanding ourselves, it makes a big difference, for example, for some people, I would say, if there's purpose to the universe or no purpose to the universe. And if the universe was created by some divine intelligence, or if it spontaneously came into being. And these are interesting questions. And as I describe in The Universe from Nothing in my new book, it's quite possible that we could create everything you see without any divine intervention, and that should change our perspective of our place in the cosmos.
Well, I have a question. If we came from exploding stars, does that mean if we came from the same exploding star that we would be related or connected?
Well, our atoms are related. Our atoms are already related for reasons I'll explain to you in a moment. But it turns out our atoms have probably been through many stars that have exploded. Our sun is fairly young. It's only 4.5 billion years old. The galaxy is 12 billion years old. Lots of material has been recycled through many, many stars. So the atoms in your body could have been not just in one exploding star, but maybe 10 exploding stars. But we are all related in the sense that our atoms get interchanged. Every time you take as I wrote in one of my books called Atom, every time you take a deep breath, you're breathing in at least 2 or 3 atoms from the dying breath of Caesar when he said tu Brutus. And in fact, you're connected to almost everyone who's ever lived. Every time you take a breath, and every time you take a sip of water, you're drinking atoms that were excreted by almost every slimy thing that's ever lived on Earth in its history. Think of that next time you take a drink.
Well, let's talk a little bit about which universe do we live in. You've written that there are 3 types of universes. There is an open one, there is a closed one, and there is a flat one. I particularly like the open universe, but explain to us how did you come up to your conclusion here?
Okay, well, because matter and energy can curve space, it turns out space can exist in one of 3 different kinds of geometries, which we indeed call open, closed, or flat. And it's hard to picture them because we're talking about a curved 3-dimensional universe, and we're 3-dimensional beings, so it's hard to picture curved spaces. I can draw curved 2-dimensional surfaces, and we can understand them. The surface of a sphere is a closed 2-dimensional surface, for example. But it's hard to picture a closed 3-dimensional universe, except I could say that in a closed 3-dimensional universe, if you look far enough in one direction, you'll see the back of your head, for example, because space would close upon itself. And a flat universe is not flat like a pancake. A flat universe is the universe you always thought you lived in. It's the universe of common sense. It's the universe where light travels in straight lines, and the three axes, X, Y, and Z axes, always point in the same directions throughout the whole universe, just like you would imagine in a nice, sensible 3-dimensional space. Yeah. A curved 3-dimensional universe is one where the 3 axes actually point in different directions in different places in the universe, and light doesn't travel in straight lines. And one of the reasons I got into cosmology is because I wanted to know which universe we lived in, because we used to think that which universe we lived in would determine the future. It would determine how the world would end and how the universe would end, and that's one of the reasons I got into cosmology. It seemed like I wanted to be the first person to know how the universe would end. It seemed like